before humans could reach the darkest depths. Before science could understand life where light does not exist. There had already existed a mysterious world where all the rules are different. Hidden beneath thousands of meters of water, live strange creatures, predators that glow in the darkness. And life forms adapted to extreme pressure and absolute cold. A world beyond understanding, silent and full of mystery, the deep ocean. Welcome to Deep Ocean, the mysteries of the ocean abyss. Please give us a like and subscribe to the channel to motivate us to create more quality content. Don't forget to leave your comments below so we can discuss together. Let's begin. The global ocean covers 71% of our planet's surface and houses a vast and mysterious realm within. Here, beneath the shimmering surface, lies a bustling oasis full of life, where every creature plays a crucial role in the complex dance of survival. However, 90% of the ocean is located in a silent place, hidden from human sight. In the deeper layers below, the ocean is the domain of a much stranger world, the deep sea. This is a world within our world, a place of silence, emptiness, and darkness, where wonders float in an endless void. At the upper limit of the deep sea lies the twilight zone, where the dim sunlight is still enough to dominate biological processes. This zone extends from 200 meters to 1 kilometer beneath the waves. But since the average depth of the ocean is nearly 4 times greater, and the deepest known point is at 11,000 meters, the twilight zone is only a thin layer. The next layers of the ocean occupy a much vaster space. The midnight zone, or bathypelagic zone, extends to a depth of 4 kilometers. It is a place so deep that the direct influences of the sun, waves and tides are imperceptible, creating a habitat that has remained almost unchanged for millions of years. At its lower limit begins the abyssal zone, where a giant mud desert at the bottom of the ocean called the abyssal plain is found, a realm of mud-dwelling creatures. Only in a few places in the world does the final underworld of the ocean sink even deeper, through great cracks created by plate tectonics. These are the oceanic trenches, or the Hadal zone. When it comes to deciphering secrets, each of these layers poses a greater challenge than the last. But that does not prevent us from striving to explore, with a degree of success even though the majority remains an enigma. Since the late 20th century, manned and remote-controlled vehicles have granted access to the deep ocean. Like this device, the ROV Sebastian, a robot owned and operated by the Schmidt Ocean Institute. It is the size of a small car, and with a depth capacity of up to 4.5 kilometers, its operating range covers the entirety of the midnight zone. Controlled from the surface via a cable, Sebastian illuminates the abyss and reveals a glimpse of the hidden space beneath the ocean's surface. As the ROV descends into the midnight zone, we begin to find strange creatures that look like nothing seen near the surface. Some are so small they're hard to see with the naked eye, while others are giants. This is a place of pure darkness, too deep for any light to penetrate. It is an extreme environment where the physical distance from phytoplankton, the base of the food web, limits the number of animals the midnight zone can sustain. Life here must find ways to operate in a cold and dark abyss where the temperature does not exceed 4 degrees Celsius and withstand extreme hydrostatic pressures ranging from 100 atmospheres at the top of the zone to 400 atmospheres at the bottom. Despite these challenges, animals must make trade-offs and push their morphology and physiology to the extreme to avoid predators, search for food, and locate mates amidst a vast black void. For this reason, a series of surreal adaptations have emerged. Soft bodies, such as those of the cusk eel, can withstand the crushing pressure that would damage or kill most other organisms. Metabolism slows down significantly. Time passes at a slower pace here. It is the patient and the slow who live the longest. The Greenland shark, belonging to the sleeper shark family, is known for being able to live for centuries at depths of 2,200 meters in the icy waters of the Arctic Ocean, and growing larger than the great white shark, reaching up to 7 meters. Like many species down here, they exhibit a phenomenon called deep-sea gigantism. It is the tendency of deep-sea organisms to grow to sizes that far exceed those of their shallow water relatives. Occupying a predatory niche seems almost impossible to maintain in a place where food is scarce, even for detritivores. Therefore, to conserve energy, predators adopt the sit-and-wait strategy, taking advantage of the darkness. A ctenophore deploys a network of tentacles that do not contain stinging cells, but rather adhesive cells to trap prey as if it were a spider web. Bands of fine cilia run the length of its body and beat synchronously, allowing the ctenophore to swim and refract light into shimmering waves. They also create their own light from special cells called photocytes. This bioluminescence is likely a means of attracting prey. Another species of lobate ctenophore lacks adhesive tentacles. Instead, it uses cilia to create water currents that suck in food. At depths of 2,000 to more than 4,000 meters below the sea, where pressure can exceed 400 times that of the surface and the surrounding water temperature is only 2 to 4 degrees Celsius, columns of black smoke unexpectedly emerge from the Earth's interior. At hydrothermal vents, superheated water that can exceed 350 degrees Celsius gushes out continuously, carrying metals and energy-rich compounds, creating oases in the middle of a frozen desert. Around these chimneys, life concentrates with a density rarely seen. Schools of shrimp can cover the surface with a density of thousands of individuals per square meter. Giant tube worms up to 2 meters tall stand upright, while crabs and bottom fish move between the cracks of the hot rocks. Here, chemosynthetic bacteria play the fundamental role, using hydrogen sulfide to generate energy instead of sunlight, providing the source of life for the entire ecosystem. Without light and without depending on the sun, these ecosystems can exist for decades around a vent until the heat decreases. During that time, they create one of the most unique forms of biodiversity on the planet, where life does not come from the sky but is born from the Earth itself. At the bottom of the ocean, where the ground is not static mud but erupting black chimneys, a completely different world exists. From the fissures of the Earth's crust, superheated water, rich in minerals and metals, gushes out at temperatures that can exceed 350 degrees Celsius. These black smokers turn the seabed into a landscape that seems like both hell and the cradle of life. No light, no photosynthesis, only chemistry and thermal energy. And in the midst of this seemingly uninhabitable environment, dense schools of shrimp congregate around the vents. The Rimicaris shrimp is one of the most extreme adaptations ever recorded in the deep ocean. Their bodies are small, only a few centimeters, but they concentrate in thick groups, covering the surface of the chimneys like a moving living layer. They almost no longer depend on vision. Their eyes have degenerated into organs that detect dim light, just enough to perceive the weak radiation emitted by the vents themselves. Instead, their lives are tied to a special relationship. Inside the shrimp's branchial cavity, there are symbiotic bacteria, organisms capable of using chemicals like hydrogen sulfide to produce energy, completely replacing sunlight. The shrimp does not hunt in a conventional way. It raises these bacteria and harvests them as its main food source. Living near the vent means existing on the border between two worlds. Just by getting a little closer, the temperature could destroy living tissue. By moving further away, the source of chemical energy disappears. Therefore, these shrimp move constantly, adjusting their position centimeter by centimeter, keeping their bodies in the ideal temperature zone, a thin line between life and death. Not only shrimp, but an entire ecosystem exists around these volcanoes. Giant tube worms, crabs, fish, and microorganisms form a complete community, all dependent on chemical energy. This is one of the few places on Earth where life exists totally independently of the sun. In the grand picture of the ocean, these small shrimp act as the base of a special food chain. They transform inorganic energy into biomass, feeding the entire surrounding ecosystem. A closed system that operates silently thousands of meters deep, where humans are just beginning to understand. Between the eternal darkness and water currents as hot as lava, life not only exists but thrives under completely different laws. And here, small creatures like the Rimicaris shrimp prove that life always finds a way, even in the most extreme places. There is also a clear tendency in the color of fish here compared to the twilight zone. Silvery and shimmering fish decrease. Instead, a series of dark brown or black fish predominate. Many species possess an adaptation called ultra-black, with surfaces covered by melanosomes containing extremely high concentrations of melanin, which reflect less than 0.5% of light. This contrasts sharply with the reflective guanine crystals of twilight zone fish. Where being too dark would only make their silhouette stand out more under the residual sunlight. Down here, that is a superpower. The luminous organs located under each eye of this loose-jaw dragonfish produce red bioluminescent light that acts as a beacon. Bright red prey, which normally appear black at these depths, become clearly visible under the red light. The black-bellied dragonfish renounces the ultra-black color and chooses a bronze-colored skin, using a luminescent barbel on its chin that acts as a lure. The large, backward-facing teeth of the viperfish are too large to fit in its mouth. But they act as a cage, ensuring the prey cannot escape once captured. Its fangs are made of crystalline nanostructures so small that light wavelengths pass through them instead of scattering, making them invisible. Decorating the belly of the dragonfish are bioluminescent spots used for counter-illumination, matching any light coming from above when viewed from below. The Pacific blackchin fish has only been filmed in its natural environment a few times. In many of these encounters, it remains motionless, perhaps to avoid detection. Like the bronze-colored dragonfish, its silvery scales only shine when illuminated by the lights of the underwater robot. But in the dark, they can scatter light and hide their body shape. There is very little information about its life history, as with many species from such depths. But what is in the midnight void of the ocean? Food is too scarce to sustain aerodynamic predators. There are no rocks to hide in, nor a seafloor for miles around. Two types of bodies seem to predominate. Globular fish, such as the anglerfish, are not suited for continuous swimming, but rather for floating and waiting for prey to fall into their grasp. Others, like this sawtooth eel, have a long and flexible anguilliform body. This morphology not only allows it to hide its silhouette by hanging vertically when it ventures into the twilight zone, but also allows it to move in a series of undulating waves along its body to generate propulsion. The snipe eel moves in a similar way, but is thinner and thread-shaped. The jaws of its bird-like beak curve outward at the tips, covered in small teeth with backward hooks, to catch small crustaceans as it sweeps through the water with its mouth always open. The snipe eel also holds the record for having the most vertebrae of any animal on Earth, with more than 700 along its 1.5-meter body. When fish like this move with flexibility throughout their length, the undulation waves are transmitted backward with increasing amplitude and speed, generating the greatest propulsion at the tail. It provides the most efficient method of locomotion in an energy-starved place without sacrificing speed like the anglerfish. Not being limited to the waiting strategy allows eel-shaped fish to perform various feeding behaviors, such as the enormous mouth of the gulper eel. It is larger than the rest of its body and can open wide enough to scoop up entire schools of shrimp or swallow animals much larger than itself. A pouch-like lower jaw contains the prey, while its stomach expands inside to house and digest the feast. While in the twilight zone, bioluminescence is used for hiding. Here it becomes the voice of the lonely wanderers of this midnight world. A female anglerfish possesses a lure called an esker, filled with bioluminescent bacteria and located at the end of a modified dorsal fin called an elysium. Encounters between anglerfish are so rare that many species have gone to extremes to maximize reproductive success. They exhibit extraordinary sexual dimorphism. The male has no lure and is tiny compared to the female, but possesses large eyes and nostrils that allow him to detect the species-specific pheromones of the female. Once he finds her, the male develops a pair of pincer-like teeth in the jaw and permanently attaches himself to the female's body. Their circulatory systems fuse and the male atrophies until he becomes a sperm sac, fed and maintained by the female's blood. Efficiency is key in the ocean, and every aspect of the body structure and behavior of organisms is optimized to solve the challenges they face. Body shape makes a big difference, depending on the environment they inhabit. In the sunny waters of the high seas, predators spend most of their lives hunting. Water is 800 times denser than air and 50 times more viscous, making movement a challenge. For a predator, an aerodynamic shape with a rigid forked tail like that of a tuna is very beneficial. This is the fusiform body type. It minimizes inertial resistance and allows the tuna to migrate more than 15,000 kilometers in a year, sometimes reaching speeds of 43 miles per hour. Reef fish have laterally compressed bodies. They need agility more than speed, so they are flattened on the sides to turn quickly and precisely between coral and rocks. On the sandy bottom, fish have depressed bodies, flattened vertically. The chimera is one of the oldest fish in the ocean, an ancestral relative of sharks that split from their common ancestor 200 million years ago. Running along its entire length is the lateral line system, resembling patches used to sense movement in nearby waters. For every 10 meters we descend, the pressure increases by 1 atmosphere. To survive, fish have evolved reinforced protein structures and more fluid cell membranes to protect vital biological functions. For others, including many cephalopods, soft and gelatinous bodies are all they need to overcome the pressure and maintain neutral buoyancy. Water cannot be compressed, so being composed mostly of water offers unique advantages. The Dumbo octopus beats a pair of fins on its mantle that look like ears to move gracefully, steering with its webbed arms as it crosses the void. Reaching depths of 6,000 meters, it is the deepest living octopus. The pressure at the lower limit of its range can be 600 times greater than at sea level, equivalent to the weight of 50 jumbo jets. Although for us, the conditions of the depths seem extreme, the characteristics that define a challenging environment are always relative. For many residents down here, the ocean surface is the hostile environment, and the low pressure conditions of shallow waters would be fatal to them. In the mosaic of animal diversity in the depths, cephalopods are perhaps the most mysterious, showing physiological, morphological, and behavioral transformations to become the masters of this world. Each of them is like an ethereal dancer, pushing the limits of adaptation to create a unique existence. They dominate with many shapes, sizes, and colors, exhibiting unusual appendages for feeding. The long, sticky tentacles of the whip squid hang like flypaper toward the lower waters, in a position called tuning fork, while it enjoys its own cloud of ink. When it is time to move, the tentacles retract into a protective membrane within the squid's arms. The large eye of the strawberry squid allows it to track the silhouettes of animals above against the deep blue of the twilight zone. During the day, it resides at the edge of this zone, at about 1,000 meters depth, where the luminous background fades to black. It positions itself by rotating or flipping its body so that its second, smaller eye looks directly into the darkness in search of luminous prey. Dimorphism in the eyes of animals with bilateral symmetry is very rare, and for the strawberry squid, this is a unique adaptation that allows it to find a life niche where resources are scarce and competition is high. Now, let's return to the abyss. The boundaries between ocean layers are not sharp. The twilight zone and the midnight zone belong to the aphotic zone, defined as the depth below which less than 1% of sunlight reaches, a place often called the tenebrous ocean. While some animals adapt to the twilight zone, designed for a place where light is reduced but not completely lost, or to the midnight zone, engulfed by total darkness, others can inhabit both. In such cases, being born with a cloak of invisibility is very beneficial. Aside from the eyes, optic nerves, and a long, narrow digestive system, this glass octopus is almost completely transparent. This is a male. The small hooked tip of a tentacle is a modified organ called a hectocotylus, used for reproduction. An adult female can reach about 45 centimeters in length. Her body is mottled with pigment cells called chromatophores that she uses for camouflage. Small muscles can expand to open the pigment sacs, darkening her body. That is the mechanism behind the color-changing ability of many other cephalopods, clearly exposed through a transparent body. In the midnight zone, the feeding behavior of squids and octopuses differs greatly from that of organisms in the twilight zone. Above, in the mesopelagic zone, life passes at a fast pace thanks to the abundance of prey. Squids here hunt in groups, surrounding schools and shooting ink to confuse the fish. The largest one that does this is the Humboldt squid, which launches tentacles with toothed suction rings to catch silvery lanternfish. Scenes like this occur every night in the twilight zone, triggered by the subtlest changes in ambient light as the sun sets, driving schools of fish from the mesopelagic zone to gather and migrate vertically under the protection of darkness. This phenomenon is one of the only reasons why large, active hunters like the Humboldt squid can maintain such an energetically expensive lifestyle. In the deep bathypelagic zone, you must be an opportunist to succeed. Schools of fish are few, but sinking organic remains are abundant. Marine snow, the leftovers from feasts in the upper layers. In its velvety cloak, the vampire squid deploys a long sensory filament covered in sticky mucus to catch these fine particles. It is well adapted to a place that is not only hungry for food, but also for oxygen. Its blood contains a respiratory pigment, hemocyanin, with the highest affinity for oxygen known among cephalopods. Therefore, the vampire squid can reduce competition from other detritivores by occupying the oxygen minimum zones of the ocean. Reproduction beneath the midnight layer can also be as challenging as feeding. A black-eyed squid mother drags a clutch of more than 2,000 eggs through the ocean, contained in membranous sacs that double the length of her body at a depth of 2 kilometers. She will carry them for up to 9 months, holding them firmly with her hooks and never letting go, not even to eat. It is a once-in-a-lifetime feat, and also a dangerous one. As the eggs mature and the mother weakens, her body begins to deteriorate and her muscles atrophy. Unable to shoot water to flee quickly, she becomes an easy target for predators. Swimming is a burden, but essential. Through her movements, the mother circulates water through the eggs and provides them with oxygen. If she survives the final months, her final act of motherhood will not be in vain. Her sacrifice gives way to new life as the hatchlings begin their own journey through the indefinite void. Even so, no one knows how many of her thousands of eggs will survive to hatch their own eggs in the future. Of the more than 700 species of cephalopods known to science, the black-eyed squid is one of the few that dares to carry its offspring through the darkness. But they are not the only single parents. A barrel-shaped amphipod crustacean, or phronima, carves a home of protective gelatin from the carcass of a salp. Imagine a squirrel taking over the body of a cat. She repurposes that body as a mobile home and feeds her young with the leftover parts. Some larvae must face the darkness alone, like this bottom-dwelling lobster larva. Or the leptocephalus, the transparent larval form of the elopomorph group, one of the most diverse groups of fish, which includes tarpon, herring, and all known eels. More than 800 species of fish begin life this way, feeding on sinking marine snow particles. Some remain in this life stage for more than a year before metamorphosing. In general, the more complex the environment or structure, the more biodiversity it can sustain. But in the deep mid-column waters, where there is no structure or solid surface, the only form of shelter that can be found is in other animals. Large organisms become drifting ships, lifeboats that house a crew of smaller organisms. Some are simply stowaways. The crustaceans on this blob-top jellyfish cause little harm or impediment to the host, but benefit from having a safe place to hide. Others are parasites, like these amphipods feeding on a salp. This pelican eel carries a parasitic copepod that has coiled around its internal organs and pierced its digestive tract with spiny mouthparts. The two ribbon-like structures extending behind it are the egg chains. Inside the pouch-like bell of a deep Staria jellyfish, an Aneuropus amphipod is slowly eating the host's thin skin. It must maintain a careful balance, ensuring it does not overeat so as not to risk losing its own shelter. Deep Staria is unusual among jellyfish, belonging to the Ulmaridae group, many of which lack real tentacles. As a result, it feeds in a strange way, enveloping its prey before closing the bell like a drawstring bag. Its digestive system decorates the bell with a net-like pattern, extending finely to distribute nutrients over its vast surface. Other Ulmaridae without tentacles have developed their own feeding strategies. The big red jellyfish, Tiburonia, has a bell like a beach ball and arms as thick as fingers, covered in clusters of tiny wart-like stinging cells. The giant phantom jellyfish, Stygiomedusa gigantea, has curtain-like arms that can measure up to 10 meters, hanging in the water column. It is the largest species in the Ulmaridae group and one of the largest known jellyfish in the ocean. It is sometimes found at depths of 6,700 meters in the Hadal zone. It is believed that these arms completely lack stinging cells and are used to wrap and engulf prey inside the giant bell, which can expand up to 5 times its size. The phantom jellyfish participates in another form of ecological relationship. It forms an association with a fish called the pelagic brochula, seen here navigating the surface of the jellyfish. Stygiomedusa's large bell provides shelter for the fish, and in return, the fish removes parasites from the surface of its protector. Studies on this relationship have found evidence that the fish can return to its partner if separated. Its body possesses specialized sensory organs, neuromasts, extremely sensitive to low-frequency water movements, such as those generated by the beating of the jellyfish's bell. They work together through a mutual symbiotic association. It is a lifestyle shared by countless pairs in the natural world. In the deep ocean, The cooperative convergence of life through symbiosis is especially important because the dangers of this vast space are a challenge for everyone. However, jellyfish and other soft-bodied organisms seem to have mastered this place. They are almost perfectly adapted to a three-dimensional, structureless aquatic world, out of the reach of time. They are one of the few groups of animals that are helped, not hindered, by the lack of complexity. In this vacuum, the plasticity of their basic morphology means they can grow to extraordinary sizes. The life cycle of soft-bodied organisms in the deep sea is largely unknown. While some survive the vast space by seeking shelter in others, there is a group that seems to have found the solution to being small in such a large space, the siphonophores. This is not actually a single organism. It is rather a colony, a modular entity composed of small animals called zooids. Each of these individuals is a genetically identical clone, but their function and structure are altered through mutations so that different zooids specialize. They assume specific tasks to ensure the survival of the entire colony. Along a central trunk, these zooids attach themselves, limited to predetermined zones where they remain and perform their role. Gastrozoids are the polyps that feed. Each zooid deploys a tentacle to catch and digest food, which then nourishes the other zooids through the trunk. Nectophores look like small jellyfish. These zooids are the swimming bells responsible for coordinating the movement of the entire colony. At the top, a gas-filled float called a pneumatophore helps maintain buoyancy. Species possessing these three structures are physonect siphonophores, one of the three suborders defined by a distinct body plan. The second type are chalicophorans, which only possess nectophores and lack a gas float. This is the giant siphonophore, Priadubia. It is one of the longest animals in the ocean, reaching 50 meters. Sister necks possess a gas float and a long trunk containing gastrozoids, but lack swimming bells, resembling a frayed rope floating adrift. This siphonophore is about to do something strange. It tears off parts of its own body. Where the last light of the ocean fades into a deep and cold blue, the water surface seems to belong to another world. At depths of thousands of meters, pressure crushes any weak structure. The temperature drops to a few degrees Celsius, and darkness becomes the permanent rule. From that silent void, a colossal mass begins to move, slowly but powerfully, like an invisible force cutting through the ocean. The sperm whale appears, the largest predator of the deep sea. With a length that can exceed 16 meters and a weight of more than 40 tons, its body is designed for dives that go beyond the limit of most mammals. Its massive head occupies nearly a third of its body and contains spermaceti, a special structure that helps control buoyancy during deep dives. But its true value lies in the capacity for echolocation. the extremely powerful clicks it emits travel far into the darkness, bouncing off every surrounding object and creating a three-dimensional map of the invisible world. Where light does not exist, sound becomes the eyes. Starting the hunt, the sperm whale takes a long breath at the surface and dives, without rushing, without wasting energy. In its body, oxygen is stored efficiently in the blood and muscles, allowing it to dive to more than 2,000 meters and remain there for more than an hour. In total darkness, sound signals bounce off soft floating bodies. Giant squids. As the distance shortens, the rhythm of the clicks accelerates, turning into a series of frantic signals. It is the moment of attack. The giant body accelerates, the jaw expands, and in a single movement, the prey disappears into the infinite void. The circular scars on the whale's skin are traces of fierce confrontations where the prey is also not weak. They are not always alone. In shallower waters, female sperm whales live in pods, communicating with a series of complex sounds like a language of their own. They protect their young, maintain social structures, and transmit survival experiences through generations. Meanwhile, adult males separate, venturing into deeper waters where the largest prey reside. A natural division of roles that helps the species make the most of all ocean layers. In the ecosystem, the sperm whale is at the top of the food chain. By hunting deep-sea squids and fish, they control populations and maintain the balance of the deep ocean ecosystem. But their influence does not stop there. Every time they emerge and dive, they transport nutrients from the bottom to the upper layers, contributing to feeding plankton ecosystems. In a world where most beings must shrink or save energy, the sperm whale chooses the opposite path. It dives deeper, hunts larger prey, and adapts to the darkness in a way that no other being can. And when it disappears into the abyss, the ocean seems to return to its original state of calm. The relationship between the giant squid and the sperm whale is one of the greatest confrontations on the planet. The circular scars from the suckers on the sperm whale's head are hard evidence of life and death battles in the depths. While the giant squid tries to defend itself with its spiny tentacles, the sperm whale, the predator with the largest brain in the world, considers them its favorite food. It was from remains in the stomachs of sperm whales that scientists gradually reconstructed the portrait of the giant squid's real size and power. Until the beginning of the 21st century, the giant squid was one of the few species of large animals that had never been photographed alive. What we knew came from specimens washed up on the shore. It was not until 2004 that the first photos of a live giant squid in its natural environment were taken in the twilight zone, at a depth of about 1,000 meters. And although we don't know much about these mysterious creatures, we know they are enormous. The largest individual ever found was 13 meters long, like a school bus and weighed 275 kilograms. Compared to most squids that do not exceed 60 centimeters, these giants are exceptional. Scientists believe that by possessing such size, they have few enemies and can quietly hunt deep-sea fish and other squids. But as impressive as the giant squid is, it is not the largest. The colossal squid, sometimes called the Antarctic squid, is the largest invertebrate in the world. They have a shorter length than the giant, about 10 meters, but can weigh between 500 and 700 kilograms. Lurking at depths of more than 2,000 meters, it is easy to imagine a creature as massive as a fierce alpha predator. But this squid teaches us something different about the giants of the deep. They are not necessarily the dominant predatory force we imagine, because with great size comes something else, an extremely slow metabolism. From the eternal darkness of the abyss, we gradually return to the layers where light filters again through the ocean. Sunbeams pierce the water, drawing shimmering columns in the blue immensity. And here, in the middle of this seemingly empty space, a colossal silhouette appears. It is not a predator of the darkness, but the largest being that has ever existed on Earth, the blue whale. At more than 30 meters long and weighing almost 180 tons, the blue whale's body exceeds all the biological limits we know. Its heart is the size of a small car, and every beat can be heard kilometers away underwater. Despite its massive size, its aerodynamic shape and thick layer of fat allow it to move surprisingly well. It glides through the ocean with a smoothness that generates almost no resistance. The bluish-grey color of its body blends with the scattered light underwater, making it hard to recognize despite an impossible-to-hide size. But what makes the blue whale special is not that it hunts giant prey. On the contrary, its survival strategy is based on tiny, almost invisible organisms, schools of krill, where each individual measures a few centimeters, grouped together in dense living clouds. When the moment comes, the blue whale accelerates from below, expanding its gigantic jaw in a powerful lunge. Dozens of tons of water, along with the prey, flood its mouth. Then the water is expelled through the long baleen plates, retaining millions of small beings inside. A single mouthful can provide an immense amount of energy, enough to feed the largest body on the planet. This feeding behavior is repeated hundreds of times a day during the season of abundance. The blue whale migrates thousands of kilometers each year, following the currents of nutrient-rich waters. In the seemingly empty world of the open ocean, it reads subtle signals from the environment to find the places where life is concentrated. Although it is a giant, the blue whale does not live in absolute solitude. The low-frequency sounds it emits can travel hundreds of kilometers, helping it communicate across the vast distances of the ocean. They are slow, deep, and prolonged signals, like the breath of the ocean itself. In the ecosystem, the blue whale acts as a crucial link in the nutrient cycle. By consuming large amounts of krill and then releasing nutrients at the surface, it contributes to fostering the growth of plankton. Its presence is not just a symbol of power, but an engine that maintains life on a global scale. In an ocean where size usually means predatory ferocity, the blue whale chooses another path. It does not dominate through violence, but through the ability to exploit small but abundant resources. And when that colossal body slowly disappears under the luminous waters, the ocean becomes calm once again. As if it had just released a giant sigh and then locked all its secrets away.